In this video, I want to look at substitution at sp2 centers. Now here I have an alkene, it's chloroalkene, cyclohexene with a chloride on it, and I have a nice thiol here. Thiols are really good nucleophiles. And the question is, can we substitute this sulfur for that chloride? Now how would we do that? Well, if we're going to do a substitution reaction, we have to attack the substrate at some sort of empty orbital. Where's the LUMO of an alkene? Well, it's that pi bond. So basically the sulfur would have to attack the pi bond, which means it's going to come down from the top. So it can't do SN2 type chemistry here on this alkene. It's going to have to simply attack the top. And so what kind of an intermediate we're going to get? Well, we can't just do that. We've got to put that negative charge someplace. So where we put the negative charge? Well, we just have to put it on the other carbon. So this would be our intermediate. And how does this look? Well, it doesn't look good at all. Naked carbon anions are not at all stable. This is not a good species. That is not a good intermediate. You need some better place to put that negative charge. So this reaction simply won't work. You can't just do a substitution on a normal alkene. Can you ever do a substitution on an alkene? Well, yes, you can if you choose an alkene which has a place to put the electrons. What's good for putting where would you like to put electrons? How about we introduce a carbonyl? Carbonyls are great for picking up electrons. So now we have a conjugated carbonyl with a chloride down there. Let's do the same reaction again. Well, again, we'll attack the carbon. Now we'll push the electrons not onto the neighboring carbon, but up here into double bond position, because we can push the electrons out onto the oxygen. So what we've done is essentially we've parked those electrons in the intermediate out on the carbonyl. This is a perfectly good intermediate. It's a nice tetrahedral intermediate. It should remind you of the kind of intermediates you had when you talked about the substitution of acid chlorides. So now we can just finish up our reaction by bringing back those electrons, and we're going to have to lose the proton as well, and the order here is not terribly important, but basically what's going to happen here is these electrons are going to come back. We're going to swing over, reform our double bond. We're going to kick out that chloride, and of course we're also going to lose the proton there. So let me just straighten this out a little bit, okay, and do a down arrow here. And we have done our substitution reaction. So like I say, this is very much like doing a substitution reaction on an acid chloride. You get this nice tetrahedral intermediate. And so this you would call is conjugate substitution. Substitution on an alkene, but only on an alkene which is in conjugation with a carbonyl. Now what I want to do next is I want to carry this over and do it in an aromatic system. So let me draw out an aromatic system. This is going to be a little bit specialized. I want an electron withdrawing group, and I'm going to use a cyano group. It's not necessarily the best one, but it's one of the easier ones to draw. So for our first example, we'll do a cyano group. And let's say we have a chloride down here. Whoops, sorry, in the meta position. So here's our substrate, and we'll use that same thiol that we used before to do the substitution. So here's our thiol, and let's see if this works. Can we park those electrons? So what I'm going to do, okay, is I'm going to have the sulfur come and attack at this carbon. We've got to push these electrons over. Now we can push them into double bond position over here. That doesn't help much. This would of course just push the double bond up here. Okay, this would and we're just going to go around the circle. There's nothing we can do, because there's no way we can get those electrons out onto the nitrile. If so, whoa, we're just stuck. We're going to have a very ugly system here. This doesn't work at all. That's crazy. We can't do that. What are we going to do? Well, the best we can do is take one of these electrons and just basically park it on the neighboring atom. So this this is the best we can do. We get this negative charge. It has no stabilization. Now we can, and this of course is because it's meta. So let's forget this meta nonsense. It's not going to get us anywhere. Let me go over and instead of meta, let me move this chloride to the para position. And as you might not be surprised, now it's going to work. So we're going to take our thiol, attack the chloride. Now we can take the electrons nearby, push them up to this double bond. We can take this double bond, push it out onto the nitrile, take the triple bond, push it onto the nitrogen, and now when we draw our intermediate, okay, we have a perfectly good tetrahedral intermediate. My isn't quite straight here, but anyway, here's our nice tetrahedral intermediate, and of course we can do the same kind of thing that we just did before. We can bring those electrons back and kick out the chloride. So we'll just do that. We'll reform the triple bond. We'll reform the aromaticity. We'll come back to the double bond here, and we'll kick out the chloride. That's a little bit overlapping here. Let me move this around a little bit so we can see it better. I don't want to do that. I want to do this. Okay, here's a better set of arrows. And of course, at some point, we've got to kick out that hydrogen. I'll just do it the same step. Okay, so this is our substitution product now, and this is called now. This is going to be called nucleophilic aromatic substitution. Nucleophilic aromatic substitution, whereas the ones we did earlier were electrophilic, because this is attacked by a nucleophile, not an acid. Now the nucleophilic substitution will only work if you have a place to park those electrons, and so what you need is an electron withdrawing group. That electron withdrawing group has to be in the para position, or not surprisingly, the ortho position. It can't be in the meta position, or don't do you any good. So to do nucleophilic aromatic substitution, what you need is a good electron withdrawing group and a good leaving group, ortho or para, to that electron withdrawing group. Then you can carry out the reaction. So it's a neat reaction if you can do it, but it's a little bit more specialized than the electrophilic aromatic substitution that we did first.